Okay. Let's now understand how this carbon dioxide laser works. Let's now go back with this in mind, with this energy level diagram in mind. We will now go back to the setup once again. This is how the setup is. This is the power supply. Okay, this is the power supply where power is supplied, and this is where CO2 and N2 are there with and helium in the ratio 1 is to 2 is to 3 with some water vapors, of course. So now what happens is, when you take CO2 and N2, that will have that energy level structure which I just showed, and a huge power is supplied. Okay, when a huge power is supplied, what will happen in this is, please remember, there are no metastable states here, but the first excited state of nitrogen, that is N2 molecule, is metastable. And what is a metastable state? Metastable state is something which has wherein the whole thing wherein the atoms stay there for longer. Okay, so as usual, the construction is, a CO2 laser consists of this will consist of 2.5 centimeter discharge tube of 2.5 centimeter in diameter and 5 meter length. The schematic is shown here. The tube is filled with CO2, nitrogen and helium in the ratio 1 is to 2 is to 3, and some traces of water vapor or hydrogen is added. The two electrodes are provided in the tube for the application of electrical energy as the pumping source. This is very important, and the pressure inside is maintained at 6 to 17 torr. Torr is the unit of pressure. Now working. Now how does this work? This works when a suitable power supply, when a suitable voltage is applied across the electrodes, a glow discharge is initiated in the tube. So due to this glow discharge, what happens is, if you look at this, due to this glow discharge, during this discharge, many electrons are rendered free from the gas atoms. Okay, this is what is known as ionization. These electrons will come ripping apart from the atoms. These free electrons accelerated, since these are negatively charged, they get accelerated towards the positive electrode, and in the way they collide with N2 and CO2 molecules. Okay, see, there are N2 and CO2, remember, in the discharge tube. So they will collide with N2 and CO2 molecules. During the collision, some part of the energy of the electron gets absorbed by the gas molecules, that too especially by N2. So the N2 molecules are sitting here. Now electron comes and hits here. A part of the energy is absorbed, and this goes, when it absorbs the energy, where it must go, it cannot stay anywhere here because the energy is quantized. This takes the energy and goes to the higher energy state. Okay. Now you have something of a situation in which these CO2 molecules are sitting here. N2 absorbs the energy and goes to the higher state, but remember, this is a metastable state. And not only that, this is a metastable state, the energy of this first excited state of nitrogen exactly coincides with the first excited state of symmetric stretch. This is, remember, this is symmetric stretch. First is the symmetric stretch. This is bend, and this is asymmetric stretch. These two completely coincide. So what happens? There is a the huge, since it's a metastable state, the molecules remain there for relatively longer time. So let me repeat once again. As the discharge is initiated, there is a process of ionization, and electrons move towards the positive electrode, and in that process they will end up colliding with N2 and CO2. These N2 molecules absorb that energy and go to the higher state. This is a metastable state, and by definition metastable state is a state where the atoms will remain longer, right? So since there is a close coincidence with the E5, okay, since there is a close coincidence with E5, which is one of the energy, which is the excited energy levels of one of the modes of CO2, they collide with the CO2. And one more thing, when I say this is E1 and E5, don't think this of a spatial separation. This is not a spatial separation. This is only an energetic separation. Don't think that the ground state is atoms are sitting here and the excited state atoms are sitting here. They could be sitting one next to each other, but it only says that this has less energy and this has more energy. This will be vibrating, this will not be vibrating. So this will be, if this is not vibrating, this is in the ground state. If this is vibrating, this is in the higher state. So all are together only. They have that proximity. But few are energetic, few are not energetic. The few are excited and few are not excited. So what happens now is, once this metastable state is there, so these molecules absorb energy and go to the metastable state, and they since they are in close coincidence with 001 state of CO2, CO2 when it collides with CO2 molecules, that is what is shown here. N2 star is the excited state of N2. It collides with CO2 molecule, gives all its energy to the CO2 molecule. That makes this CO2 molecule, since the energy difference is same, this makes this CO2 molecule to climb this. Okay, so this is N2 is highly energetic, as you can see. N2 is already in the first excited state. It collides with CO2. It gives all its energy and comes back. Okay, it is non-excited, but it excites CO2, which is in the ground state. So all these atoms are now in this state. This is how we have achieved a population inversion. Since this is metastable, their atoms will stay longer. By collision, they will give their energy and de-excite, and CO2 molecules get excited again. Okay, so now now the population of CO2 increases rapidly, and these levels are designated, as I told, by these levels. Once the population inversion is established in E5, then what happens is, there is a stimulated emission from E5 to E3. A stray photon or a stray packet of energy can initiate a stimulated emission for E3 and E4. The population inversion is achieved here. So any photon will bring down 2, and you will have 2 photons emitted, one for E4 and one for E3. Okay, so this will give out a laser of wavelength 10.6 mu meter, and this will give out a laser of wavelength 9.6 mu meter. Now E3 and E4, after going here and coming here, E3 and E4 are the levels where the atoms are living in. The transition from E4 and E3 levels to E2 level occurs through the collision with ground state molecules. The depopulation of E2 takes place through the collision with helium or water molecule. Remember, we had also mixed helium and water molecule. So from here to here, the depopulation occurs. Once again, CO2 is in the ground state. Once again, the same process happens, and this is how a CO2 laser is produced. Essentially, you will have a laser of 2 different wavelengths. One is 9.6. This is a transition. This is a stimulated emission between E5 and E3. If this stimulated emission happens between E5 and E4, you will have 10.6 mu m to be the wavelength of the laser. So essentially, let me repeat the entire thing once again for the sake of clarity, so that it will become absolutely clear. So in this discharge tube, we are going to take CO2, N2 and He and water vapor in the ratio of 1:2:3. This is the first thing. Power supply will pump. Okay, when you start the power supply, there is a discharge. Okay, there is a discharge, and what that discharge does is that will separate electrons from the atoms. This is called ionization. Since electron is negatively charged, it will move towards the positive terminal, and in that process it will collide with nitrogen and CO2 molecules. The cavity consists of nitrogen, CO2, nitrogen and helium in the ratio 1:2:3, and water vapor or water, right? Water vapor or water, the traces of water vapor. So this is the energy level diagram. Since the energy is quantized, the nitrogen molecule can vibrate here or here. CO2 molecule has three different modes in which it can exhibit energy. One is called symmetric stretch. It can symmetric stretch here or here. The bend is ground state is here. For the ground, this is the ground state 0, 0, 0, first excited state, second excited state, nothing in between. This is bend. And asymmetric stretch is asymmetric stretch here, the energy could be here or here. This is the energy level diagram. Now when the discharge is switched on, due to the ionization, those electrons will collide with N2, and N2, due to the collision, the energy is transferred to nitrogen, and nitrogen will, all the molecules of nitrogen or many molecules of nitrogen which have got that energy will go to the first excited state. This first excited state is a metastable state. Metastable state is the state where it will remain for the longer time, and by collision, that is what this equation, since this level and the fifth level of carbon dioxide match with each other, by collision, N2 star, which is the excited nitrogen, will collide with CO2 so that it gives all its energy to CO2. CO2 gets excited in the sense that the molecules which are in the ground state will go to the fifth state, E5, and sit here. Since this is metastable, there is a and energy and the excitation is happening to through collision. Here the population inversion is reached. Due to this population inversion, a stray photon can induce a stimulated emission. In fact, two such emissions are possible. One between E5 and E3, and E5 and E4. Between E5 and E3, you will get a laser of wavelength 9.6 mu meter. Between E5 and E4, you will get a laser of wavelength 10.6 mu meter. Then by itself, the it will come back to E2, and here, due to the mixture of helium and by helium, the depopulation of level E2 takes place through the collision of these CO2 molecules with helium and water molecules. That gets it de-excited, and it will come. Once again, this entire process starts, and this is how the whole thing gets going. And this is a carbon dioxide laser is a high power laser. Unlike the semiconductor laser, it can produce powers as high as 10 kilowatts. It has very high efficiency of about 40%. So this is the story of carbon dioxide laser. Very important as far as examinations is concerned. The question will be describe the construction and working of carbon dioxide laser. Now quickly, two uses of lasers. Usually these lasers are used, the two main usages which are listed in the syllabus are in the defense laser rangefinder system. There is a monitor, this is the laser receiver, this is the target. Since these beams have directionality property, what they will do is, rangefinder works on the principle that the distance is velocity into time. As you might be knowing, S is equal to Vt. The laser beam is transmitted through the target, and the reflected laser beam from the target is received, as it is shown here. Okay, the receiver is shown here. The time elapsed between the transmitting laser and receiving beam is measured. If f is the distance of the target, then the range of the target, means the distance it is situated, is V into t divided by 2. V, you know, the laser travels with the speed of light, right? This is S is equal to V into t. So in practice, computer aids all these things. The very calibrated devices are there, so you can have easily locate this happens so fast that you can easily locate tankers, fighter planes, guided missiles, and all those things. This is one of the uses of laser. The second use of laser is in the data storage of CDs. Okay, that is what I have shown here, using of laser in the storage of CDs. What are these CDs? Usually these compact discs or DVDs are made up of three layers. Okay, thin circular layers of about 12 centimeter diameter. They contain three layers. Okay, the first layer, the bottom layer is made up of polycarbonate. As you can see here, the bottom layer is made up of polycarbonate, which is tough and brittle. Above that there is an aluminum layer. This is the aluminum layer that is coated with plastic. This aluminum layer is coated with plastic and lacquer. Okay, now what happens is the bottom layer, which is made up of polycarbonate. Now the storage of data using laser beam is done by burning it. Okay, so wherever the laser burns, as I have shown here, wherever the laser burns the top layer, that is called as pits. Wherever it is not burnt, it is called as land. These pits denote 0 and these lands denote 1 along the spiral track. It burns along the spiral track. A laser beam is sent here. Wherever you have to mention, wherever you have to have a land, or land is usually 1 and pit is usually 0. As you know, all our information is stored in the series of zeros and 1, binary. Okay, anything can be decomposed in the series of zeros and 1s. When you have this, you can decode this. Means laser, wherever it burns, it will create a pit, and that is 0. Wherever it is not burnt, it is 1. So the string of zeros and 1s can be etched on this compact disc using the laser, and the same laser can be once again used to read it. So the same string of zeros and ones can be retrieved from this compact disc, so that you can once again convert it into from binary to any language, decode it, so that the information is preserved on this. These are the two uses of lasers which are mentioned, and the storage capacity of compact disc could be 700 megabytes, and the DVD could store up to 4.7 GB, and all these things are there. So data can be reproduced by scanning the pits and lands along the spiral track by a low power laser. Okay, and an electronic circuit generates zeros and ones, and decoder converts this binary into the original data. That is the essential process of storing the information in compact discs. With this we complete module 4, and thank you for your patience.